true, then we can infer a quadratic functional. So if we make this assumption, and a lot of times this is true, right? A1, these are our data. If we write it in tensor form, you know, for example, if it's a permeability tensor, if we just choose our coordinates correct, we can always choose it where these guys are 0. So anyway, it's always symmetrical. So I had it in my notes to show you what the quadratic functional is, but I don't think it's not that important. You know, but if you wanted to solve it with Ritt's method, you could. So let's let C call it C because it's our matrix of constants, right? And D will be an operator vector. So in other words, if I multiply this by a scalar u, then what I get is okay. So D's an operator. So using those definitions, you can write things more compactly. Which that becomes, right, if we use those definitions, then I get something nice and compact, which is why it's convenient to write it like that. This is also the weak form. So for the finite element model then, you can get the, because we wrote it down, the variational problem, we can get there rather rapidly, right? We're just going to say that u is approximately u of h, which is a function of x and y, is equal to nj uj, and del u is equal to ni. So the n's are now functions of x and y, right? And these are unknown coefficients. And all we have to do is plug those into these equations, right? All we have to do is plug them in. So I guess technically we're going to sum from I equals 1 to n. And then, of course, this whole thing is our stiffness matrix. This is our Fi. This is our Qi. So we get, in the end,
The summation should be over I or J.
I, right? Because they're J. There should be a UJ here, right? Technically, UJ. Sorry, because right, we substituted this in for U, right? But these are just constants, so I pull them out, right? But so that these are already, if I multiply it back through, then I already have a summation on every term over J. Right? So those go away. So then this becomes for the I equations. Right? Actually, no, that's not even true. If we use the Einstein notation, then that doesn't even need to be there. It's fine. Right? We're good. So there's I equations, right, like this. Where I is the number of nodes in the element. So finally, we can write in matrix form where K is equal to the integral of B transpose C B dx dy. F is integral N transpose F dx dy. Q is surface integral transpose Q N. And B is that differential operator applied to our shape functions. Right? So then what you get is N1 comma X, N2 comma X, N comma X. So this is just a matrix of the derivatives of the shape functions and the shape functions. So it's pretty convenient when you if you want to code it. If you code it in a language that can do matrix operations for you, then this is a convenient way to do it. Otherwise, if you're coding in C or Fortran or something, C++, it's actually easier to just use the additional notation.
That's not to say if you're using containers with metadata, you could just...
No, you can. You can do that too. But then you'd have to, yeah.
Or Armadillo is really easy.
I mean, there's, like in Deal 2 library, all the operators are overloaded. So you just define those to be tensors, and then you just multiply them together. It's smart enough. I guess I meant if you're just using the standard template library. And not writing your own data structures. Probably easier to do it in additional notation. All right, so I was hoping to get to the interpolation part, but I won't have time today. So next time, well, actually, I won't be here Monday or Tuesday, so you'll have some videos to watch, and those videos will cover